In the present lecture, we will discuss the introduction and basic concepts of thermodynamics. Let's start with definition of thermodynamics. Thermodynamics, it is made of two Greek words. One is thermi, another one is the dynamics. Thermi means heat, dynamic means it is power which is equal to the work divided by time. So thermodynamics is a subject to study of convert the heat energy into the work. So thermodynamics is the science of energy transfer and its effect on the physical properties of substances. What do you mean by substance? A substance refers to a material or matter whose thermodynamic properties can be analyzed. It can exist in solid, liquid or gas phases. So the aim of this thermodynamic subject is convert the disorganized form of energy, which means heat energy, into the organized form of energy, which means work energy, in a efficient manner. So aim of this thermodynamics is convert the heat energy into the work. Let's consider one example to understand the thermodynamics, and example is pressure volume work. Let a cylinder is filled with water at V1 volume and initial pressure is P1. Now heat is added to water which is in a closed container. Then water absorbs the heat and starts to boil and forming the steam. Then this steam expands due to increase in internal pressure. Now piston moves up to the volume V2 and doing the work on the surroundings, and work equal to the P into change in volume, that is V2 minus V1. So here observe the heat energy is caused to increase the volume of the water and work done by the piston on the surroundings. So thermodynamics is the science of heat energy transfer and study the effect of this heat energy on the properties of substances. And thermodynamics laws and principles are widely applied across all areas of energy technology. Some key applications are steam and nuclear power plants, internal combustion engines, gas turbines, air conditioning, refrigeration system, gas dynamics, jet propulsion, compressors, chemical processing plants and direct energy conversion devices. Let's see the outline of the thermodynamics subject. In this subject, we will discuss the following concept. First one is the basic concepts of thermodynamics and zeroth law of thermodynamics, first law of thermodynamics, first law applied to flow process, second law of thermodynamics, entropy, availability of energy, properties of pure substances. So these are the concepts we will be discuss in the thermodynamics subject. And the reference textbook for the thermodynamics is Thermodynamics by P.K. Naag. So first we have to start with the thermodynamic system. A thermodynamic system refers to a specified amount of matter or a defined region in a space selected for analysis in a given problem. So thermodynamic system refers the certain specific amount of the mass or the definite region of the space. Next we have to look for the surroundings. Surroundings is the anything external to the system is known as the surroundings. And boundary is the separation between the system and surroundings is known as boundary. So universe is the system plus surrounding is called as the universe. So it is the schematic representation of the system, boundary, surroundings and the universe. So here system is separated to the surroundings by boundary, and universe is the consideration of system plus surroundings. And this boundary may be either fixed or moving. A system and its surroundings together comprise a universe. So universe is the system plus surroundings. Let's see some examples of thermodynamic system. First one is boiling water in a covered saucepan on a stove. Here system is the water inside the saucepan, and surrounding is the kitchen air, stove and everything outside the saucepan. And boundary is the inner walls and lid of the saucepan, which separates the water from the surrounding. So let's see another example. So another example is the cold drink can left on a table. So here system refers the cold drink inside the sealed can, and surrounding is the air around the can, table and the room, and boundary is the metal wall of the can. Let's see the different types of systems. First one is the closed system. Closed system is a system of fixed mass, which means mass does not cross the boundary, although energy may be transferred into the system or out of the system. So this is the schematic representation of the closed system. Here system is consisting of fixed mass, and this mass does not cross the boundary. So it is the fixed one. But here energy is transferred, it is into the system or out of the system. And let's see some examples of the closed system. First one is a certain quantity of fluid in a cylinder bounded by a piston. And another example is pressure cooker on a stove. So in this example, mass does not enter or leave, and energy, that is heat, is transferred from the stove into the cooker. So the pressure cooker is a closed system because the mass stays inside, but energy can be transferred across its boundary. Next we have to see another system, that is the open system. An open system is a system in which both mass and energy can cross the system boundary. So this is the schematic representation of the open system. So in the open system, mass also cross the boundary. So mass is into the system and also mass out of the system. Similarly, energy also cross the boundary, energy into the system, and moreover energy out of the system. And most engineering devices are typically open systems. For example, in a air compressor, air enters at a low pressure and exists at high pressure, with the energy transfer occurring across the system boundary. See another example for the open system. Boiling water in a open pot. So here mass transfer will be occur, that is water vapor escape into the air. Similarly, energy transfer also occurring, heat is added from the stove. Next we look for the isolated system. An isolated system is a system in which neither mass nor energy is allowed to cross the system boundary. So in the isolated system, there is no mass transfer, moreover there is no energy transfer. It is having the fixed mass and energy. So this is the schematic representation of the isolated system. So here there is no mass transfer will be occur, and moreover no energy transfer also occur. Let's see the one example for the isolated system. A perfectly insulated thermos bottle. In this case, there is no heater enters or leaves. Moreover, no matter enters or escapes. So this is the comparison of the different types of system. So in the closed system, there is no mass transfer and energy transfer will be occur. So examples are the piston cylinder. Similarly, another type of the system is open system. In open system, mass transfer as well as energy transfer will be occur. Example is turbines, compressors, etc. And next, another type of the system is isolated system. In this system, there is no mass transfer and there is no energy transfer. So examples are the universe, rigid and insulated container. Next we look for the control volume. Control volume is a fixed region in space through which mass and energy can enter or leave, and this control volume is used to analyze the open systems like turbines, pumps or compressors, where the fluids flow in and out. So if the system is defined in the terms of the quantity of matter, then the system contains the same matter and there can be no transfer of mass across its boundary, calling as the closed system. So if a system is defined in the terms of the quantity of matter, then the closed system becomes the which contains the same matter and there is no transfer of this mass across its boundary. Similarly, if the system is defined in the terms of region of space within the prescribed boundary, then matter can be cross the system boundary. We are calling as the open system. So however, if the system is defined in the terms of the region of space, then matter can be cross across the boundary. This is we are calling as the open system. So these are the definitions: closed system and open system in the terms of the system is defined in the terms of quantity of matter, and similarly system is defined in the terms of region of space. So now we have to look for the control volume and the control surface. So for the thermodynamic analysis of an open system, such as consider the air compressor, then certain volume in space surrounding the compressor is known as the control volume. So you have to see this schematically. Certain space surrounding the compressor we are calling as the control volume. And similarly, bounded by a surface is called as the control surface. So in the schematic you have to see. So this is the control volume and this is the dotted line or the control surface. Now matter as well as energy crosses the control surface. So air compressor is the open system. Obviously mass and energy cross the boundary. Then a closed system is a system closed to matter flow through its volume can change against a flexible boundary. So in a closed system, so mass is the constant but volume can be changed. Similarly, when there is a matter flow, then this system is considered to be a volume of fixed identity, that is control volume. So if you are considering the volume is fixed, that is we are calling as the control volume. So there is the no differences between the open system and the control volume. Next we will discuss the different approaches of thermodynamics, that is macroscopic and microscopic approach of thermodynamics. First we have to look for the macroscopic approach. So macroscopic approach is studies the overall behavior of a system by observing the measurable properties like pressure, volume, temperature and energy. So in the macroscopic approach, so we are studying the behavior of a system by observing the certain properties, that is pressure, volume, temperature and energy. And in the macroscopic approach, so we are measuring these properties without considering the behavior of individual molecules. So macroscopic approach deals with the bulk properties and no need for the molecular level details. And in the macroscopic approach, measurements are direct and practical. And in the macroscopic approach, use the average values. Let's see some example. Analyzing the pressure and temperature of gas in a piston and cylinder device. For example, so I have to observe the properties in the terms of the pressure and temperature of the gas. We have to express the average pressure. So not we are expressing the individual molecule pressure. So here we have to express the pressure, that is the average value. Similarly, temperature also average value of the all the individual molecules. So next we have to look for the microscopic approach. In the microscopic approach, focus on the behavior of individual molecules or atoms and uses the statistical methods to relate the microscopic behavior to macroscopic properties. So in the microscopic approach, considers the kinetic energy, velocity and position of the molecules, and for this one requires the knowledge of molecular physics. And in the microscopic approach, uses the probability and statistics and explain the properties like entropy, temperature at a deeper level. Let's see some example. Density, we know density is the ratio of mass to the volume. Now mass is expressing in the terms of number of molecules. So this is the microscopic approach. Next we look for the thermodynamic properties, processes and cycles. First one is the thermodynamic properties. So thermodynamic properties are the measurable characteristics of a system that define its state and can be used to describe its energy and physical condition. So these are some examples of the thermodynamic properties, that is pressure, temperature, volume, internal energy, entropy, enthalpy, density, etc. So based on these thermodynamic properties, we can define the state of the system and its physical condition. And these thermodynamic properties are the two types. First one is the intensive properties. Second one is the extensive properties. So first we have to look for the intensive properties. Intensive properties are independent of size or mass in the system. For example, pressure, temperature, density, thermal conductivity, viscosity, etc. So these properties are not depend on the size or mass of the system. And one more thing, so density is the intensive property. So generally we know, so density is the mass divided by volume. Here mass is there and volume also there. So mass and volume are the extensive properties. But when you divide them to extensive properties, the ratio remains the constant regardless of the system size. So density is the intensive property. So next we have to look for the extensive properties. Extensive properties are dependent on size or mass of the system. If the system size changes, these properties changes proportionality. Which means if the size and the mass changes, these extensive properties also changes according to the proportionality. So let's see some common examples of the extensive properties. First one is the mass and volume, internal energy, enthalpy, entropy, heat, work and total moles. So these are all properties are dependent on the mass and size of the system. And one more thing important here, specific properties are extensive properties per unit mass and these properties are intensive properties. So these specific properties are intensive properties, that is specific volume, specific enthalpy, specific internal energy, specific entropy. So these are all the coming to the category of intensive property. And one more thing you have to remember, ratio of two extensive properties is an intensive property. For example, density is defined as mass divided by volume. Here mass is the extensive property and volume also extensive property. But density is the ratio of these two extensive properties. So density is an intensive property. Next we look for a change of state. A change of state refers to any operation that changes one or more properties of a system. Which means while any operation which changes the properties of the system. That is why we are calling as the change of state. Next one is the path. Path is the sequence of states through which a system passes during a process as it goes from initial state to final state. So path is the sequence of states of the system from the initial state to final state. So path shows the how the system changes, and it is represented on the property diagrams like PV and TS diagrams. So next we have to look for the thermodynamic cycle. A system is said to have undergone a cycle if the initial and final points are the same, and minimum number of processes required for a cycle is the 2. So let's see the schematic representation of the thermodynamic cycle and the process. So here figure represents a process and a cycle. So A to B is the process, which means it is the path which is having the changes of the state from the point A. So system having the P1 volume and the V1 volume. Let's consider at the point B, system having the P2 volume and the V2 volume. And we have to look for the another one cycle, that is 1 to 1. So 1 to 1 is the cycle. Here initial and the final state, both are having the same points. Let's consider first point is the initial one and final one as the first point. So initial and final points are the same when the system is undergone a cycle. So for a cycle, change in property is equal to the 0. So these are the basic concepts of the thermodynamic. In the next lecture we will discuss another few basic concepts of the thermodynamics. Thank you.